Discrete probability distributions may be used to extract information from a large group of discrete random variables. First, the expected value of a discrete random variable may be calculated using its discrete probability distribution. The symbol EX means the expected value of the random discrete variable x. The Greek letter mu is also used as a symbol for expected values. You might recall that this is the same symbol used for the population mean, and that is because the expected value of a discrete random variable is its population mean. It is obtained by multiplying each possible value by its respective probability and summing these products. The formula for the expected value of a discrete random variable, big X, is the summation of the product of x sub I, okay, the product of x sub I, and the probability of big X being equal to x sub I. Okay, again, it is the summation of the product of x sub I and the probability of big X being equal to x sub I. The x sub i's are the values the random variable big X assumes with positive probability. Let's compute for the expected value of the discrete random variable number of patients of 4 put under control using the antihypertensive drug. Okay, so the expected value, or EX, will be equal to, okay, what's this 0? 0 is the value of X sub I, okay, or this one, 0, times the probability that big X is equal to x sub I, which is 0.008, plus x sub I, in this case 1, times the probability of x being equal to 1, or 0.076, and we'll just continue this until we finish the whole probability distribution. So observe here that we are just getting the weighted average of the discrete random variable, and the weights being the probability. So weighted because these are the weights, and then these are the values that the discrete random variable assumes. So if we compute all of these, we get an expected value of 2.8, which is also our population mean. So this means, on average, about 2.8 hypertensives would be expected to be brought under control for every 4 who are treated. So this is from a population. This is from what the company assumes because it made a previous study on the drug that it produced. The expected value may be compared to the sample mean. Okay, so they can be compared. In our example here, we are comparing the expected value to the sample mean where 100 doctors. If you can remember, the 100 doctors were used, okay, by the company to test their antihypertensive drugs. So this time we are going to focus on the sample, so the frequency distribution table. So in order to get the sample mean, we do the same procedure in getting the expected value. So we have here the possible outcomes, and here the frequency distribution. So we simply multiply them. Okay, so here we have 0 times 0.000, and then here we have 1 times 0.090, and then 2 times 0.240, and then 3 times 0.480, and lastly 4 times 0.190. Okay, if you have your calculators and if you can solve this, this will be equal to 0. This one will be 0.090. This one will be 0.480. And then this one will be 1.44. And lastly, this one is 0.76. And if we sum these up, because we're going to add them, okay, weighted average, our sample mean here is 2.77. So if we compare that with our expected value a while ago, what was the expected value? Expected value was around 2.88, if I'm not mistaken. Okay, so you see that they are more or less close with each other. The variance of a discrete random variable may also be solved from the probability distribution. The variance obtained is the population variance, or sigma squared. Okay, this variance represents the spread relative to the expected value or population mean. And then this is the equation for solving the variance of a discrete random variable. Okay, so notice the variance of our discrete random variable x is sigma squared, the population variance, which is just equal to the summation of the product of the difference between x sub I and the expected value squared, and the probability of the discrete random variable being equal to x sub I. And then the standard deviation of our random variable is just, of course, the square root of the variance of the discrete random variable, or also known as population standard deviation, or sigma. Now let's solve this example. So this one is from a different data set. This is not the one for hypertension, the antihypertensive drug. This is the one for the otitis media, if you can remember that example. Okay, so let's solve for the variance and standard deviation here. But first and foremost, we cannot solve for the variance and standard deviation without the expected value. So let's solve first for the expected value. Let's just put the expected value in this small section here. And let's just take advantage of the arrangement of these columns. to get the expected value. Okay, so the expected value is just the outcome here times the probability of getting that outcome. 0 times 0.129, that's 0, plus 1 times 0.264, which is 0.264, plus 2 times 0.271. Okay, so that's 0.54, if I'm not mistaken. And then we have 3 times 0.185. That's 0.555. Then we have 4 times 0.095. And that's 0.38. Plus 5 times 0.039. That's 0.195. Plus 6 times 0.017, and that's 0.102. So if we add all of these, we have an expected value of 2.036. So this is important in getting the variance. In order to get the variance, remember what we need to do? First, we need to subtract the mean that we just solved here, or the expected value, 2.036, from this first outcome, so 0, and then we square that, times the probability when the discrete random variable is 0, which is this one, so 0.129. Then we repeat this summation, okay? Next will be 1 minus the expected value squared times this probability plus, okay, 2 minus 2.036 squared times this probability plus 3 minus 2.036 squared times this probability plus 4 minus 2.036 squared times 0.095 plus 5 minus 2.036 squared times 0.039 plus 6 minus 2.036 squared times 0.017. Okay, so it might seem long, but it's really just a repetition of procedures. So if you have a calculator and you simplify all of these and add them all, hopefully you'll get something like 1.967. So this is our sigma squared, or the variance of our discrete probability distribution. To get the standard deviation, that's just the square root of our variance, or the square root of 1.967, and that's 1.402. Okay? So, it's stated here that approximately 95% of the probability mass falls within 2 standard deviations, or 2 sigma of the mean of a random variable. So what that really means is, When we say within 2 standard deviations of the mean, remember our mean a while ago was 2.036. When we say within 2 standard deviations, meaning to say we need to add or subtract 2 times our standard deviation from our mean. Sorry, this is 402. Okay? And if we do this, there are 2 possible answers. When we subtract 2 times the standard deviation from the expected value, that's going to be a negative value. And there is no negative value in here. In fact, the lowest value is 0. So this is 0. Next, what about adding 2 times 1.402? Okay? When we add that, that's gonna be equal to 4.84. And since 4.84 falls short of 5, then this stays as 4. Okay? So, if we are asked this question, find A and B such that 95% of the infants will have between A and B episodes of otitis media within the first 2 years of life, those A and B will be, as we solved here, A will be 0 times, and B will be 4 times. Now, if we want to test that that's indeed true and 95% of the infants indeed fall within that, then we'll just need to add all these probabilities. So try adding 0.129 to 0.264 to 0.271 to 0.185 and then to 0.095. So from 0 to 4. If you add all of these, you'll get something like 0.944, or that's around roughly 95%. So indeed, roughly 95% of the infants would fall within these cases, 0 to 4 cases of otitis media within the first 2 years of life. The cumulative distribution function of a discrete random variable is similar in concept to the cumulative frequencies you computed for the frequency distribution table for height that you performed in Excel. Okay? So, we have here a probability mass function. This table here is the probability mass function from a population. Okay? What is a cumulative distribution function, or a CDF? Okay? The basic idea is to assign to each individual value the sum of probabilities of all values that are no larger than the value being considered. Okay, so what does that mean? So we have here an example. So let's compute for the cumulative distribution function for this probability mass function over here. Okay, so it might look something like this. If x is less than 0, less than this, meaning to say somewhere here to the left, what is the cumulative distribution function? Okay? And that is defined as the probability of x being less than or equal to small x. And small x here is less than 0. So what is that probability? You don't need to think for that. Absolutely 0, nothing. Right? There's no probability of having less than 0 otitis media. Okay? Next, the probability of the CDF when x is lesser than 1 but greater than or equal to 0. Okay. Take note, the upper value here is 1. Okay. And our CDF is defined as the probability of our discrete random variable being less than or equal to that value. And what is that probability? To the left of 1, or simply the 0.129. What about this one? When x is less than 2 but greater than or equal to 1. So of course, we look again here. This is our upper value here, the 2. And of course, the probability will be to the left. So you just need to add this plus 0.129, and that gives us 0.393. And then we continue. What about if x is less than 3 but greater than or equal to 2? This is now our upper value. And of course, we stop here because of this definition. And then we add these 3 probabilities now, and this one will be 0.664. And if we continue doing that, here our upper value is 4. So we add everything from 0.185 to the first one here. That's 0.849. And then here our upper value is 5. So this one. So we add everything from 0.095 to the back, to the left. And that gives us 0.944. And of course, we have everything. Okay, for the upper value is 6. If the upper value is 6, of course, you start from this probability, 0.039, and you add everything to its left. You get this cumulative distribution function. And lastly, if x is greater than or equal to 6, okay, if that's your CDF, then of course your upper value is beyond 6. Okay, it's beyond 6, so you need to add everything. And if we add all these probabilities, what do you think is the sum? The answer will be 100% or 1. So we can graph this one using this particular graph. And you can see, you can interpret this graph as 12.9% of the infants, or 0 to 2 years of age na child, that's 0.129 probability of having at least one case of otitis media in that span of 2 years. And obviously, having a case of 6 otitis media or lower, right? In a span of 2 years, in the first 2 years of life, 100% of children aged 2 experience that one. And that is kind of obvious if you think about it logically, right? Okay. If you include all possibilities from not having a case of otitis media to 6 cases of otitis media in the first 2 years of life, that's practically all